of this variation can just be due to the fact that we're not picking the first arrival. So here's another example of shear wave velocity versus depth. Okay, there is obviously some amount of scatter here. Not bad for geophysical data. You can see the velocities start out at about 100 meters per second. This is an area in Illinois. They start out at about 100 meters per second, maybe a little bit more above a 5-meter depth. And as you go up to 30 meters, we're getting up in this area into 200 to 300 meters per second. And so here's an example near St. Louis of a depth profile of different shear velocities, ranging from 162 meters per second in the first 5 meters down to 343 meters per second at 30 meters. The bedrock itself, we're not sure what the velocity is going to be. They haven't really made a measurement down in that because it's really hard to punch a cone penetrometer down into solid rock. You can punch it down into the soft stuff, but once you get down to the bedrock, it's really hard to do anything and make any measurements. So, what do we have on these things? These are the horizontal shear logs. These are the cone penetrometer surveys. And this is actually a in-hole suspension log. Suspension log looks like it's the most stable measurement. And then you can see the cone penetrometer and the horizontal shear logs around that. They generally follow the same curve, but there's a lot of variation. So what do we use the shear velocities for? Well, we're basically using them to predict regional site properties. For example, if I know the velocities at a certain core location and I can correlate the geology from point to point, I can take a surface geology map and actually convert it into a shear wave velocity map. Yeah?
So in the graph of the stepwise measurement, this is nothing.
Pardon?
The stepwise measurement, is that so?
No. No, that is a separate logging measurement, so that's a suspension logging measurement rather than an average log rate. And that suspension logging is typically much more accurate than the cone penetrometer or the horizontal crossel measurements, or more stable, I should say. All right, so anyways, we're taking the surface geology, a correlation or several correlations between boreholes and the surface geology, and then we're making a shear wave velocity map. So this is the shear wave velocity map, or the soil site class map, from the shear wave velocity that was generated prior to the logging, or the shear wave measurements. Here's what happens afterwards. And what you'll see is that there's been a lot more classification from C to D. Okay, so we've actually converted a lot of soil here that had relatively high velocities in the 360 to 760 into yellow. Right? Now on the other hand, we've actually converted a lot from B to A, so we've actually made it even stiffer. So we've increased the variation in this by making the measurements, but the key here is that this will be used for construction operations. We're basically giving the engineer an idea of what kind of material he has on the surface so he can design his buildings, his or her buildings appropriately. Okay, I'm not going to go into the problems now, but what I'm going to say, and we talked about this last time, is that all of these techniques require a borehole. And depending on the cost of bringing this equipment out to a borehole and drilling a borehole and site access and everything else, it might be more cost effective to utilize things just at the surface. And that's where we get into Rayleigh waves, these coupled PSV waves that have a depth dependence, that's a function of the wavelength over here, and the velocity is somewhere around 92% of the shear velocity. And again, the key characteristic of this Rayleigh wave is that it exhibits velocity dispersion. All that means, dispersion means that the shear wave velocity, or the Rayleigh wave velocity, changes with frequency if the actual soil velocity changes with depth. So if you have a soil that doesn't change, if that short wavelength arrival over there, or wave, gives you the same velocity as the long wavelength, there's no vertical variation with depth, then you won't have dispersion. Only if you have velocity that changes with depth will you have dispersion. And that dispersion can go either way. Typically, we're looking at velocities that increase with depth. Soil gets more compact. But as we talked about last time, permafrost would be an example of velocity decreasing with depth. That would give you a completely different dispersion curve. All right, now I'm going to go to the other slide. And these slides will be posted in a, they will be posted. Mm-hmm. Yeah, that's a good question, Fred. Either in the crosshole, or in the surface to borehole, or in the borehole suspension logging, those frequencies are substantially higher than the surface wave measurements. And that's a really good point. So, remember, we look at that shear modulus and we say, could that shear modulus itself be a function of frequency? Well, if we're measuring a velocity or a modulus by that equation that's at a higher frequency, it may not be representative of what it is at, say, the frequency that an earthquake occurs. Whereas a Rayleigh wave isn't quite there, but it's closer to the frequency that you want to measure at. A lot of the big earthquakes, the big vibrations are occurring between 1 and 5 hertz, or even lower than that. We probably don't capture that in our Rayleigh wave measurements that well at the moment, but at least it's close. Okay, so here's a picture of what happens when what do I receive at the receivers if I have a seismic source? And we've talked all about this before. We have an air wave, we have a direct wave, B, we have a surface wave, or Rayleigh wave, C, we can have reflections, D, we can have refraction, E, we can have all kinds of other stuff. For example, if there's some kind of discontinuity, we can have backscattering of surface waves, we can have backscattering of refractions, we can have scattered reflections. Depending on the subsurface geology, we can have a real mess down there in terms of the waves that we actually record. The other thing that we always have to be cognizant of is that we have ambient cultural noise. Now, if we're in the middle of nowhere, that may be virtually nothing. But if we do any collection of seismic data here, that's a big deal. As a matter of fact, what Nella and I are postulating right now is that the biggest noise sources in an urban environment are actually freeways, highways. And if you know where the freeways are, you essentially know where the largest sources of noise, if you were to put seismograph down, say, outside, maybe up on the hill somewhere, you might expect that the largest energy is coming from Highway 2480. Not always the case, but if you think about continuous noise, that's probably is the case. And we'll see that when we go out to the field. By the way, talked about this last time, but this kind of denotes what happens as a Rayleigh wave propagates across the ground. And any of you that have been in a big earthquake have probably even seen the ground move like this. I was in the Loma Prieta quake, and you could actually see the rolling humps if you were in a field coming at you. And they would shake the trees, and the trees would go up and down, but it's basically like an ocean wave coming at you. Pretty interesting. You could see that the motion of the wave, you probably can't see it, but it basically goes in an ellipse like this. So it basically has a compressional motion and a shear motion. So again, here's a picture of the wave, and what we're trying to denote here is not only that the particle moves in an elliptical path, that elliptical path can actually reverse direction, but you can see that the motion decreases with depth. That's that e to the minus z over lambda component of the surface wave. Okay, so let's go on to a bunch of records. All right, so time along the vertical axis, offset along the horizontal axis. What do you see there? What arrivals do you see? First of all, what's the dominant frequency in the arrivals? Can you take a look at